Hello everyone. Once again I welcome you all to MSP lecture series on transcendental chemistry. I started discussion on oxidative addition and reductive elimination reactions, and in my previous lecture I showed a scheme in which I considered many substrate molecules which can undergo oxidative addition or which perform oxidative addition on a metal. And let me continue from where I had stopped. So, this is the scheme yesterday I wrote. You can see the difference between few substrates and their addition onto the metal center. For example, if you see hydrogen is added on sideways, that is in a cis manner, and then if you look into oxygen, that is also added in a cis manner. So, that means oxygen or hydrogen, when they are added, first they go and sit something like this, and then they split into two anionic ligands. And then if you just look into Me3SiH, trimethylsilane, it also follows the same sequence, and then another one is these three. But look into other 4 reactions here. So, just to differentiate the chlorine or chloride ligand that is coming from the substrate molecule and also one that is already present, I have given different colors. Let us look into this one here. If you see, this one is coming here and this one is coming here, that means they are added trans positions on iridium moiety. And then if you look into mercury chloride, again same thing, it is added here and here. And then if you look into typical addition of hydrogen halide, that also they are going to opposite ends, and same thing is true in case of methyl iodide. That means why that is happening like that? It is not just with these substrates. If you consider substrates such as SnCl4, this can also add like SnCl3 and Cl, and then if you consider CH3 SO2 Cl, this also adds this one separately, transpositions on iridium here, or if you take CH3CO Cl, these two fragments will be added after this bond is broken, CCl bond is broken, and if you take even this one, so this will be added like that, or if we consider this one, this splits and this is added and this is added separately, and then there all trans addition will be there. So, with this now let us try to understand the different methods or mechanism through which one can perform oxidative addition reactions. I have shown here oxidative addition mechanism can be broadly split into 2 categories. One is 2 electron mechanism. So, another one is single electron mechanism. Within 2 electron mechanism, you can notice 3 different type of oxidative addition reactions. One is SN2, one is ionic, one is 3 centered cis addition. Of course, the moment the term cis you see here, you can correlate this one with, we saw few substrate molecules in the previous scheme, which are the substrate molecules which are added onto the metal in a 3 centered cis concerted manner. This is called 3 centered concerted addition. In case of single electron mechanism, we can come across radical mechanism, and also radical mechanism can be further split into chain and non-chain mechanisms. So, now let us try to understand these mechanisms one at a time. To begin with, let us focus our attention on 3 centered cis addition. Of course, whatever the mechanism I have written here has to do something with the class of substrate molecules we are choosing. You recall I made a statement that all substrate molecules can be divided into 3 classes. One is non-electrophilic, and the second one is non-electrophilic intact, and the third one is electrophilic. So, whatever the substrate molecules you are thinking that they can do or perform oxidative addition on a metal will fall into one of these categories. So, now with this information, let us look into the mechanism of addition through 3 centered concerted addition in which the two anion ligands will go to cis positions on the metal center. So, now that means the oxidative addition reactions can be classified into broadly 3 types. One is 3 centered concerted additions, nucleophilic oxidative addition of RX, that means polar molecules, and radical pathways. So, that means when we perform oxidative addition, substrate molecules while adding follow one of these pathways. So, let us consider 3 center concerted addition. Here whether you consider HH bond, whether you consider CH bond or CC bond, all these additions are taking place in this type of mechanism. They have very similar one, also I wrote many other BH, SIH etc. Let me write a typical 3 centered concerted addition, again considering viscous compound and simplest molecule H2, because it is very vital in organic reactions. So, start here, iridium is in +1 state and this is a 16 electron species, and start with it is a D8 species. Now, this is 3. So, iridium is in +3, and if you count electron it is 18 electron species and it is a D6 system. So, that means this is what exactly happens here. Initially, so this H2, before it is getting ready for oxidative addition, it has to be pre-coordinated to the metal center in this fashion, and then it abstracts 2 electrons from iridium to generate 2 hydride anions and they will be added. So, here oxidative addition is complete. So, if you see here this intermediate, this one we have D8 system, we have still iridium is in +1 state, and then this is an 18 electron species here. This is an 18 electron species here. Okay, this is fine. Now, let us look into 2 aspects. One is electronic aspect and another one is thermodynamic aspect. So, how this thermodynamics can explain formation of this 2 iridium hydride bonds by breaking one HH bond. So, here you should remember one equation that you are all familiar with. So, now we have to find out these entities from this oxidative addition reaction to calculate the value of free energy. Okay. So, in this reaction first let us look into delta H naught. So, in order to calculate this one, what we have to see is in the reaction, if you see, we have broken one HH bond and we have formed 2 new iridium to hydrogen bonds. Formation of 2 iridium to hydrogen bonds and then breaking of one HH bond we should consider here. For this one, if you put the values that are available, this is -16 kilocalories per mole or mole inverse. Okay. So, now we have to calculate delta S. Of course, if you look into that reaction, delta S is large and negative because H2 gaseous one it is disappearing, and in that place we are getting a solid. This is very large and negative. So, this is minus 30 entropy units, or this is equivalent to minus 125 joules per mole per Kelvin. Of course, temperature is 25 degrees centigrade. Now, if we incorporate this to calculate delta G, what we get is minus 16 minus 298 into 30, of course to convert that divided by 1000, what we get is minus 7 kilocalories per mole. So, what does it indicate? If you look into delta G, it is very small. It is very small. That means if the delta G value is anywhere between plus or minus 10 to 15 kilocalories, with appropriate reaction condition, one can think of reversing that reaction. That means the way we add H2 through oxidative addition, we can get rid of H2 through reductive elimination. Okay. So, that means reaction may be made reversible under appropriate condition. So, that means by using an appropriate reaction condition, we should be able to reverse this reaction. So, that means if we get an idea that we can reverse the reaction, then the catalytic application automatically comes into the picture. That means here this reaction can be used. So, that means whether we are bringing back the same H2 or we are taking the H2 source to bring back the complex that was underwent oxidative addition, that is a different thing. Okay. Always one can do that. What one can get from this thermodynamic calculations is this reaction can be reversible. Now, let us look into the kinetics involved in this one. Of course, here the rate depends on the concentration of complex as well as H2 substrate molecule here. This rate constant is consistent with a concerted process. You can see here, this is the reaction coordinates I have shown in this one. To start with, we have iridium 1 complex here, and then after H2 is added, it forms a transient species where it is a neutral ligand binding through these 2 electrons between 2 H atoms, and then enthalpy here is for this one is about 10 to 12 kilocalories per mole, and then once oxidative addition is completed, we get this iridium 3 complex here. This is quite stable and the difference is about minus 16 kilocalories per mole. So, that means basically any reaction in this one overall delta G is about minus 7 kilocalories per mole. So, this thermodynamic aspects tell us about the reaction and whether it is exothermic or endothermic, and if the delta G of that particular reaction or conversion is well within reaching well within 10 to 16 kilocalories per mole, it can be made reversible. Now, let us look into how, for example, I had mentioned earlier, you take a olefin and add hydrogen under high pressure in a closed reactor and then heat it for several hours, but still hydrogenation do not proceed completely, and probably you can get 5 to 10% of olefin converting into hydrocarbon. Whereas the same reaction one can do it in presence of a metal complex such as viscous compound. In some cases you can achieve 100% hydrogenation at lesser temperature under less hydrogen pressure with ease. So, that means something conventionally it is not possible. How that can be done using metal complex. That means we have to look into this thermodynamic aspect as well as electronic aspects and also the bonding and how metal initiates breaking of HH bond. It is not easy. So, that means here I will show you a molecular orbital picture here. This already I showed you when I was talking about the classification of ligands by donor atoms under hydrogen ligands. So, here this H2 molecule having 2 electrons between 2 HH and then that interacts with the appropriate metal here. So, say D8 system. In this case what happens, this 2 electrons represents the sigma bond between metal to hydrogen H2 molecule here, and then it depends whether we retain this as a neutral ligand or how quickly or how slowly this is split into 2 anions to form 2 metal hydride bond can be seen here in this case. Once a pair of electrons are donated from through sigma bond, what happens, HH bond would be weakened. Okay. So, HH bond something like this is there, it starts elongated, okay, after coordination, because now the electrons are not really residing between these two to hold this H together, H atoms together. Instead what happens, electrons are moving towards the metal through sigma donation, it is elongated. Now because of back donation, sigma star is pulling electrons from one of the orbitals. Here it is say xz we have taken one, you can take xz, yz or xy, one of those things, and to begin with this is the HOMO for metal, highest occupied molecular orbital, and now this is shared between sigma star by generating a pi bonding and anti-bonding orbitals. So, now basically what happens, we are taking out a pair of electrons between 2 hydrogen atoms through sigma bonding. Not only that one, that weakens the bond, in the same time we are also adding electrons to the sigma star anti-bonding orbital. So, that means these 2 kinds of bonding affects HH and eventually HH bond is broken very nicely. So, this you cannot imagine when we are simply taking in a conventional reaction an olefin and H2, when the metal is placed, the moment H2 comes near the metal, what happens, electrons between 2 H are pulled and the electrons from metal is added to sigma star. 2 kind of loss suffered by H2 results in the breakage of HH bond completely, and thus oxidative addition will be completed. So, that means sigma donation from filled H2 to sigma orbitals to metal orbital, and then pi back donation from metal orbitals to H2 sigma star orbital. This eventually results in HH bond cleavage. So, these 2, and of course the next question is it possible to still use H2 as a neutral ligand and by preventing its oxidative addition? Yes, it is possible. Then we have to consider following aspects: metal with positive charge, and metal should be in higher oxidation state or containing good pi acceptor ligands, but cannot back donate well. So, that means when the metal is positively charged or metal has higher positive charge, it is a reluctant pi donor, and again metal is in higher oxidation state, it has electron deficiency, as a result it is a reluctant pi donor. And also if we have very strong pi acceptor ligands already present on the metal like carbon monoxide, they take lion's share of metal pi orbitals, pi electrons towards it, so that less number of electrons are left for back donation to sigma star of hydrogen. So, that means in that case what happens, metal cannot do back donation well to sigma star of hydrogen. So, stable eta to H2 complex can be generated. So, that means yes, it is at will, you can either stabilize H2 as a neutral molecule binding to metal center, or you can split that one to generate 2 anions for completing oxidative addition reaction. I will show you a few examples here. You can see in these cases, here you can see HH bond is about to break here, and whereas here HH bond is retained, still H2 is coordinated in eta 2 fashion, whereas in this case of course we have both terminal as well as hydrides and as well as molecular hydrogen binding. So, that means as I mentioned here it is 7 coordinate and 18 electron dihydrate this one. So, here these phosphines are not very good pi acceptors compared to carbon monoxide. As a result, what happens, and pi acceptor ability of hydrogen is more or less comparable to those of tertiary phosphines. As a result, what happens, it also fights for a lion's share in the back bonding. As a result, what happens, more electrons come here and then HH bond cleaves. So, that okay, whereas in this case we have better pi acceptor ligands here, carbon monoxide, which will take lion's share and leaves very little or no electron density for the donation from metal to H2 sigma star. As a result, what happens, this H2 is retained. So, that means we have to choose what we are looking for, whether we want to break HH to add oxidatively to generate 2 hydrides, or we want to retain as a neutral. That is in our hand. We have to choose right kind of ancillary ligands with sigma donor and pi acceptor properties, and also suitable oxidation state on metal, so that we can always tilt equilibrium either way. So, now let us look into CH activation. This is one of the most important reactions in organometallic chemistry from the economic point of view, and of course, here when we try to do CH activation, we can come across 2 type of activation. One is intermolecular CH activation, it is very rare, and other one is intramolecular CH activation, very common. Okay. Cyclometallation happens here, and okay, and also this intramolecular CH activation is responsible in many reactions. Let me show you one such CH activation. So, if I want to perform CH activation here, what I should do is, first I have to vacate some coordination sites on the metal. For that one, best way would be to shine UV light, that means you do photochemical reaction. Under this condition, H2 is eliminated to generate this transient species. Now, you can see reaction, this species is ready for oxidative addition. Now, we bring an appropriate molecule having CH bond, an appropriate solvent, this is a typical CH activation reaction here. This is intramolecular CH activation, and then one can also think of intramolecular CH activation that can only happen in some cases where we are using special type of molecules, or there is some way we can generate that kind of intermediates. So, let me show that one. Let us consider a platinum complex. We have these 2 groups. Of course, before we perform any further reaction, one of the tertiary phosphine should go, and of course, this will be an equilibrium situation. You can recall, this is called some sort of very similar to beta hydrogen elimination. If you so tertiary phosphate is in solution. Now what happens, this Me4, so this CH2 is there, this will abstract this one, so this CMe3 will come out and we end up with this is one example for intramolecular CH activation. So now we should look into some aspects here. Whenever we perform CH addition, retention of configuration takes place at C if CH bond approaches metal side on. Okay. Always in a 3 bond concerted addition, always this substrate approaches in a side on position, something like this, that is shown here. So something like this, it is coming here. So in this case it forms a 3 membered intermediate, that is the reason we call it as 3 centered concerted addition, and then what happens, it breaks here and oxidative addition is completed. So in this case what happens, easier for all, especially for aryl groups, because usually with 3D, 4D, 5D if you go, metal to aryl bond strength increases, and also compared to alkyl, aryl bonds are more stable because of reinforcement of metal to carbon bond, because of delocalized electrons present on carbon, more favorable for 4D and 5D metals because they have higher metal to carbon bond strength, and intramolecular is common, intermolecular is rare, requires free site at the metal to occur. Okay, now let us look into CC additions, industrially important reactions there, and of course the cracking of unstrained carbon-carbon bonds is still limited to heterogeneous reactions, and no matter how much we talk about homogeneous catalysis, in the present scenario the contribution towards total catalysis from homogeneous catalytes is only about 16%. The 85% of the catalytic reactions are heterogeneous in nature. Whenever we talk about petrochemical industries are cracking to generate a whole bunch of organic molecules, still extensively heterogeneous catalysis is used, and strained only sometimes CC addition is possible, especially when we have very strained molecules where CC bond is very strained because of very congested 3 or 4 membered rings are there in it. Strained CC bonds undergo readily oxidative addition to remove the ring strain. One such example let us consider here. So what I am telling is, cracking means CH activation means you take something like this, and then this is called really cracking. So it is not easy to do this kind of reaction using homogeneous catalysts, and even if you do it, probably the yields are so low, and if you master this one, there is very good scope in industries to perform these kind of reactions at low temperature, especially with cheaper metals. If we can do something with iron, cobalt or nickel, yes, we are making fortune. Then I was telling you about strained rings. Let me give an example how strained rings can break CC bond and that can be added onto the metal. I am considering here well known complex here, I am sure you are all familiar with this compound. So take this compound here, metal complex, in presence of at least 2 equivalents of pyridine, and then this molecule here. This is an example for strained ring adding onto the metal through oxidative addition. So let me discuss more related to this topic in my next lecture. Until then, have an excellent time reading. Thank you for your kind attention. See you in my next lecture.